All right. So, a couple of things real quick. I'm still continuing with recording the lesson. So right now my voice is being recorded and it's going to be posted on YouTube. The links will be on Moodle. You can go and watch and re-listen to the videos. And what's great is that it's going to have my voice with the PowerPoint and all my writing on it. Okay, so I don't actually write on the board, I write on the tablet. If you can't see, let me know, right? Because I can change stuff to make it more visible. So, topic is waves. Actually, the course is called Waves, Optics, and Modern Physics. And it's a stupid name because there's 3 different topics that have very little to do with each other. And you'll see, like, we'll do waves, and then we'll be like, all right, waves are done. Now let's do optics. Then optics will be done, and we'll be like, all right, let's do some modern physics now. Like, it's really like, it doesn't really mesh well, but they still somehow have to do with, like, you'll need to know your trig. That's pretty basic. We're gonna basically today, we're gonna try to review some of that. Right. What can be described as a wave? Tell me, what have you seen in life that's a wave? There's a picture of one on the board. That is a wave, a water wave. Okay, great. What else do you think behaves like a wave? Something that does repetitive, gradual motion. Try to be creative here. I want like 10 examples. Start thinking. Yeah, that's in math. What follows a sinus and cosinus function? Yeah, sound waves, right? That behaves like a wave function. Yeah, a clock, exactly. Can you explain that to me? Yeah, exactly. So yeah, let's say we take the minute hand, and the minute hand does one full rotation, and it takes a certain amount of time, and then it does another full rotation. So that's a wave. What else? Talk about it in your groups. Give me 10 examples of wave, things that do waves. They're literally everywhere. Light, yeah, exactly. Keep going, keep going. Talk about it with your group. What's that? Microwave? Yeah, absolutely. Think along the lines of what Olivier said. Olivier said the hands of a clock. It doesn't have to be something that propagates like a wave. If that's that's the along the lines you're thinking, that's fine. But not everything is the same as like a wave being propagated, like a radio wave or a sound wave or a light wave. Some things just have repetitive motion. What has repetitive motion? Car wheel, exactly. If you take a point, if you take, that the pinhole where you put the air, and you take that the position of that as a function of time, well, that oscillates up and down or on a circle or whatever. So that's definitely something that follows a wave format. What else? Yeah, that one is a dampening wave, but it's definitely a wave. So your height with respect to time. So if you're bouncing up and down on a bungee cord. Anyone ever do bungee jumping? Anyone ever do skydiving? Which one is more scary, skydiving or bungee jumping? Who says bungee jumping is scarier? Who says skydiving is scarier? Really? That string breaks. You're gonna eat a lot of rocks. Yeah, but then you would have had the ride of your life for like 2.5 minutes. I've gone skydiving. It's a lot of fun. I would never do bungee jumping, maybe because I'm big and I'm afraid I'm just my mass is too much for the cord to handle. But I would never do bungee jumping. Anyways, so yeah, so that's definitely a wave function. How about something else? Be more creative. Give me something to do with the day. What is there in a day that could be repetitive? The sun, exactly. Yeah, the height of the sun in the sky, the brightness of the daylight. You know, it increases to a certain point, then it decreases. You get to a peak darkness, and then we get to a peak brightness, peak darkness. Repeats itself. How about in a month or in 28 days approximately, if you're following that calendar? The what? The year? The year is not 28 days. The Earth. Yeah, but what about the Earth? Those rotations. Okay. It could be like the moon, for example, right? So the fullness of the moon is a wave function. All right. I think those are pretty good. Just keep in mind that anything that has repetitive motion like that, right, is considered to be a wave. What's not considered to be a wave is digital signals. You guys know what digital signals are looking like? What's binary? Some of you computer guys. What is binary? You guys should know this. Ones and zeros. So it's either a one or a zero. So the information is given like this. This is binary, and it's not a wave function, even though it's kind of up and down. It's a square function. We'll call this a square function. So this wouldn't be considered a wave function. It has to be a gradual increase, gradual decrease, gradual increase, gradual decrease. Okay. How about if I had an object? You know, a computer does that. You know? Never figured out how to fix that. If I have a mass attached to a string and I let it go from some angle here, what is this thing going to do? It's going to oscillate in a wave function, right? If you graph its height or its distance from the equilibrium point um, with respect to time, it's going to go back and forth or up and down. If I had an object attached to a spring, and I pulled down on the spring, this thing would bounce up and down. That's a wave function. Okay? These are all the kinds of things we're actually going to be learning about this semester. Um, we're going to be doing first type of wave that we're going to be doing is this kind here, where it's kind of a wave of a physical object. And then we're going to do waves of sounds, then we're going to do waves of light, and then we're going to do like gravitational waves and that complex. It's just called complex, but it's really not that complicated. Relativity stuff, like things that have to do with quantum physics and like Einstein's string theory and theory of relativity, things like that. It's actually really super duper interesting. Like this is like cool stuff. Um, we're actually going to even do a part where we're going to prove that gravity doesn't exist. Yeah, mind blown. I taught that to my grade 9 students last year, and I had students who actually cried, and I had parents call me, "What are you teaching this stuff in class?" They weren't ready. All right, so learning objectives. You guys know this. Today we're just going to go over, or just this first PowerPoint. I think we can go over two today. We'll see how far we get. In this PowerPoint, we're going to talk about just waves, what waves are in the most general sense. We've answered this question. It's a repetitive motion. Maybe we can write that here. Repetitive motion. And if we talk about a water wave, for example, a water wave moves along in a certain direction. All right. The fact that it has a direction is actually quite important because a wave propagates, and I said that it's repetitive motion. And what I mean by motion is that it actually, there is a propagation. I have a question here. I have a statement here, but I want you to keep this in mind because I'm going to ask you a question about it later. Is that wave isn't carrying particles, it's carrying energy. Okay? Keep that in mind because I'm going to come back to it. Let's do some practice first. So over here, I've graphed two. I just did this in two because I wanted more space. I want to practice graphing what waves look like. So if I have what I have in red right there, that's sine x. Okay? And here you can see that at sine x, you have this sine function. You have the sine function that goes up and then goes back down, and then it reaches 0 again. It reaches 0 twice in that one time. And it takes 2 pi amount of x, or whatever we're going to call this time. It takes 2 pi amount of time for it to come back to its original point. And then if you cut this here, like that, and you cut this here like that, you get the exact same thing. It's repetitive. That's the thing. That's the motion that's being repeated. All right, and you can cut the same thing here. Every 2 pi chunks that you take, as long as they're adjacent, they're going to look exactly the same. So far, so good? Now, if I were to graph 2 sine of x, what would be the difference? So here, what I have already is just sine of x. What would 2 sine of x look like? Let me ask you another question. What is sine pi? No, that's not a good one. Let me ask you, what is a sine of pi over 2? 1. What's 2 times the sine of pi over 2? 2. What is the sine of 3 pi over 2? Minus 1. What is 2 times the sine of 3 pi over 2? Minus 2. So what would be the difference between sine x and 2 times sine x? The amplitude, right? So that 2 in front of it is the amplitude of our wave, right? So we have something that looks like that, okay? So this 2, so this 2 here is the amplitude. I'm going to change color for the next one. All right, so I'm removing that 2 coefficient amplitude. I'm removing this 2 here in the next one. And I'm going to call this one sine x plus 1. Okay, so we're back at sine x. I'm going to ask you the same question. What is sine of 0? What is the sine of pi? What's the sine of 2 pi? What's the sine of pi over 2? What's the sine of 3 half? 3 half pi. Minus 1. Okay. So now every time we did that, I want you to add plus 1. So you said that the sine of 0 is 0. And so 0 plus 1 is 1. Come on, pen. There we go. Is 1. Yeah. You guys said that the sine of pi over 2 is 1. 1, and then add another 1. So that's going to be 2. And then the sine of pi is 0 plus 1. That's 1. Oh, a lot of time for this thing today. There we go. What is it going to look like? What's the sine of x plus 1 going to look like? Everything, it looks exactly like sine x, but for every single value, you're adding plus 1. So what is it going to look like? Exactly, yeah. Right? It's going to be the same as sine of x. Ooh, things are shaky. That. You see how it looks like sine of x? It's just a phase upwards. It's like you took sine x and you moved it upwards. Okay? Does this kind of ring a bell? Did you guys do this in high school? Yeah? A long time ago, high school, right? Remember how easy things were? Okay, any questions about amplitude and that value here? If I were to give you sine x plus 2, what would you do? Come on, guys. You would just move it up by 2. What if it was sine x minus 1? Lower by 1. Okay, what if it was 2 sine x plus 1? Exactly. You would draw sine x, 2 sine x, your amplitude would get bigger, and then you would move it up by 1. Okay, that's what I'm trying to get. Okay, perfect. Again, I have here sine x. I drew it again. Now we're going to modify it differently. We're going to talk about sine of 2x. So what is that? How is that going to change my wave function? This one we talked a little bit about at the end of E&M last night. It's the frequency. What does the frequency mean? Is how many what? How many waves per kind of time, right? So if there is a more frequency, then are the waves going to be squished together or stretched apart? Squished together. So if I have sine of 2x here, which I'm going to do, do this in the red, all right? If I have sine of 2x, it's going to be more squished together. How many times more squished together is it going to be? 2 times more squished together. So this one, it takes 2 pi for just regular sine x. It takes 2 pi to do 1 full cycle. How much is it going to take for sine of 2x to do 1 full cycle? 1 pi, exactly. So I'm going to go like this. Kind of like that, okay? And then this goes on in negatives. This goes on until infinity, okay? So far, so good? What if I had sine of 0.5x? Or sine of 1 over 2x? It's going to get stretched out. How many times more stretched out? It's going to be 2 times more stretched out. So instead of it taking 2 pi to do 1 full cycle, it's going to take 4 pi to do 1 full cycle. Okay? All right. Last example here. That's not true. I have more examples on the next slide. What's going on? Come on. I don't know what's going on. I'm going to do this one. Sine of x minus pi. So what's the sine of 2? What's the sine of 0? 0. Okay. What's the sine of 0 minus pi? That's going to be what? Minus 1, exactly. So what this is showing you is that this is going to be a translational, what do you call this? Modification of the wave to the left and to the right. So what this is going to do is actually it's going to phase change everything towards the right. So this minus 1 that was here, it's going to be now at 0. So it's going to look like everything's moved towards the right. So it's going to look like kind of like that. So it's a translational move. I think my computer is really not cooperating today. Translation to the I give up. It's a translation to the right. So far, so good? All right. So again, I've drawn for you sine of x. Now I'm asking to you, what's going to look like if I do sine of negative x? So what's sine of pi? What sine of pi is? What's the sine of negative pi? Okay. What's the sine of pi over 2? What's the sine of negative pi over 2? Okay, so now what we're doing is a flip of the function, right? So everything that was positive is going to become negative. Everything that's become negative is going to become positive. So your function, so if we draw this in blue, it's going to look exactly like sine x, but it's going to be flipped. And what about negative sine of x? So everything that's positive is going to be negative. Isn't that just what we did before? That's exactly like what we did before here. So then you can say that sine of negative x is equal to negative sine of x. That's one of the trig identities that you might have learned when you're doing this in calculus. All right. Lastly, let's talk about cosine. So again, I have my sine x here drawn for you in this bottom graph. And I'm asking you to draw cosine of x. Cosine of 0 is what again? It's what? 1, right. So this time we start our graph at 1, and then we do the same thing, right? So the only difference between sine of x and cosine of x is just a phase shift, okay? So if I were to take this function and just move it along a little bit or move it back a bit, it's going to be exactly the same as this thing. So when we're going to talk about, because this is going to be important when we do our simple function, when we're talking about a sine of a function, you could pretend that it's the same thing as the cosine of a function, right? Because the only difference is when you start your timer. If you start your timer a little bit later, your sine function becomes a cosine function. Okay? It's the exact same shape, just shifted left and right. And the negative cosine of x is, well, the opposite of this. So I'm going to do that in a different color. This is blue. I'm going to do this in red. And so this is going to start at -1, and it's going to do something like that. Okay? It's not in phase correctly, but as long as you know that it flips, when you put a negative in front of it, it flips the thing. Okay? So far, so good? Okay. Okay, that was just review. I'm waiting until you guys are done writing. We're going to talk about time a lot in this class, and distance a lot in this class. I mean, it's physics, and what's physics without distance and time? And so we're going to add those variables into what we just learned. If I'm looking at this wave here, what's the amplitude? That's the easy one. What's the amplitude of this wave? How high and low does it go? 3. The amplitude would be 3. What's the wavelength of this? What's a wavelength? If you were to define wavelength by exactly what it's called, the length of a wave, what would be the length of this wave? That's how much? 2 pi? So let's talk about one wave. So one wave is from one point on the y until it reaches that same exact point on the y. So if we're talking about one wave, we're talking about this. That's one wave. So what was the length of that wave? 2. 2 what? Well, it doesn't actually say, but let's say this was in meters. It would be 2 meters. I love it. How about its frequency? Frequency, I'll give you a hint, has to do with time. Do we have any information about time here? So we actually can't determine the frequency. Or we can't determine the period. And the reason for that is because the axis here is in distance. If this axis was in time, then we would be able to find out the frequency in the period, but not the wavelength. All right. We'll get into examples on that later. Okay. So here we are. Can you guys see this, or is this too small? Okay. William, can you see that? Can you read it? Yeah. I can zoom in a little bit. I won't be able to write while I'm zooming in. What's important to notice here is that one of my axes here is distance, the other one is time. That allows me to talk about um, frequency and period and wavelength. So here I have distance, and the length of one full wave, we call that the wavelength, and that is symbolized by the letter lambda. You guys remember this from last semester a little bit? Maybe, hopefully. And we're looking at a wave in terms of time, one full wave, the amount of time it takes to do one full wave, we call that a period. Insert an appropriate term. All right. Now, we have how long it takes to do one wave, right? But how many waves happen per second? What is that defined as? Yeah, frequency. So this is how long it takes to do one wave. Then how many waves per second, that would be frequency. So let's just define that right here. So the wavelength is the horizontal length of one wave. The period is the time required to complete one wave. And frequency is defined as the number of waves per second. Let me ask you guys an example of that. Marker. All right, so let's say this was 1 second. From here to here is 1 second. 1 second of regular time. What is the frequency? How many waves are there per second? So it's 1, 2, 3. So what's my frequency? 3 what? What's that? I heard something good. What's the units of frequency? Think about your processors. Hertz, exactly. The symbol for frequency is hertz, Hz. What's my period? How long did it take to do one wave? Remember, it took 1 second to do 3 waves. So how long did it take to do one wave? 1/3. What are the units of period? Regular second. So that's your period t is equal to 1/3 of a second. What's the relationship between this and this? Frequency and period. What's the relationship? It's what? Inverse proportion. That's it. So you put down here, the frequency is equal to 1/period. Any questions on this? Am I going too fast? Am I going too slow? So again, we're going to talk about, I'll just erase this real quick. So periodic waves are just waves that repeat. They don't necessarily have to repeat, but they do. We talked about this. We talked that frequency is 1 over the period. It's measured in hertz, or the units right there, Hz. And that's 1 hertz is 1 cycle per second. 10 hertz is 10 cycles per second, or 10 waves per second. Okay. What is the frequency of the second hand on the clock? What's the frequency of a second hand on a clock? So let's look at the definition of frequency again. Frequency is the number of cycles per second. So one cycle is one full rotation, right? So how many of those, how many full rotations do you have every 1 second? Do you have even one full rotation in a second? No. How many, what fraction of one full rotation do you have per second? Yeah, you want to say? Not quite. 1 divided by 60, right? So it takes 60 seconds. So the period is 60 seconds. Because the second hand takes 60 seconds to do one full rotation. And how many cycles per second? Or if you have the period, you can do 1 over 60. So it'd be 1 over 60, right? How about for the minute hand? What's the period? How long does it take for the minute hand to go all the way around? You guys said it. 3,600. All right. And so therefore, what's the frequency? Just 1 over that. Okay? Yeah, very small. All right. It's a very low frequency. Something that has a high frequency. Something that has a really high frequency. Not that. But does someone have like a singing voice? Anyways, I want to ask you to sing in class. But if you have a really high frequency, that means you're vibrating your vocal cords really, 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 really fast. So there's a lot of waves per second, high frequency. Okay, that's got a low frequency. The minute hand has a low frequency because it takes an eternity for it. An eternity. It takes 1 hour for it to go right. Okay, any questions on that? We're talking about wave speed, and I'm going to just give you this relationship now, and we're going to prove it later. Not today, when we're talking about sound, I'll prove it. But what you need to know is that a wave has a speed, right? So let's say we're talking about if I were to you're gonna see this later. Let's say we're holding a string. I have one end of the string, and then there's a person standing at the other end holding that string, and I make an up and down motion. There's going to be a wave that I'm going to create, and that wave is going to travel from my end to the other end in a certain amount of time. So therefore, your wave has a velocity, right? Or for example, sound. There's a speed of sound, or light. There's a speed of light. Both of those things are waves. And you can define the speed of that wave by multiplying the frequency by the wavelength. Okay? This is frequency, and this is wavelength. And similarly, I mean, you know that frequency is 1 over period, so you can rewrite it this way if you want. It's the same, you should get the same thing. And we're going to talk a lot about the speed of sound, and I gave you the number here. We're not going to apply it maybe today, but it's 343 meters per second. You guys know off the top of your head what the speed of light is? Pretty fast. 300,000, close. Kilometers per second. Yeah, exactly. That's pretty darn fast. So it's kind of instantaneous for when we're talking about short distances. Think about it. I don't know if you've ever thought about it this way. Light travels at a certain speed, right? If I were to, are you able to catch this if I throw it at you? If I were to throw it, it took a certain amount of time for it to go, leave my hand and reach Justin. Can you throw it back at me? Right? I'm going to throw something else. I'm going to throw this because I'm afraid of breaking. If I throw it faster, is it going to take less time or more time? Less time. You ready for a faster toss? There you go. Good. Wasn't ready. So you can throw it back at me fast. Okay, thank you. And if I threw it even faster, I'm not going to do it. If I threw it at the speed of light, would it get there instantaneously? No, it would take very little time, practically instantaneously, but not instantaneously, right? That means that when light hits me and reaches you, there is a time delay. What you guys are seeing right now is something that happened fractions of a second earlier. It's like time travel, isn't it? Right? Because this is not what I'm doing right now. This is what I did 1 bazillionth of a second ago, right? Think about it. What if I were really, really far? What if I was like, because it's fast, because we're pretty close. What if I was far away? Then that time would be longer, right? For that light to reach you. Let's say I was like at the sun. How long would it take for me to do something and for you to see it? 8 minutes or whatever. That's that time thing. It's 8 minutes and 14 seconds, I believe, is the time. It takes 8 minutes and a few seconds for light from the sun. When we're looking at the sun, what we see is what happened 8 minutes ago. And when we're looking at stars, the nearest star is what we call 4.3 light years away, right? And it's called 4.3 light years away because it takes light 4.3 years to get here. That's what light years mean. So if it takes light 4.3 years to get here, when we're looking at that star, that's the closest star. It's called, you guys know the name of the closest star? Starts with a P? Proxima Centauri. Okay. When we're looking at Proxima Centauri, the closest star, that's what we're seeing is 4.3 years old. That's pretty damn old. But that's the closest star, right? And if we're looking at like the furthest points in the universe, this is how we're able to determine how old our universe is, because this is where light literally stops. It's 15 billion light years away. So we can say that our universe is roughly 15 billion years old because light after that never reached us. It's literally time travel. You're getting me off on a tangent. I find it so fascinating. All right, let's take a 5-minute break. Because you're on vacation mode? Last week we had to come in, all teachers had to come in, and we had meetings all day, every day. Like it was just horrible. What was your average wake up time during the break?
It's like
1 or 2?
no, me it's like
Okay.
9, but like I take naps. Like I don't know, like, I can't. I'm not a late riser, so like I wake up. Like right now, I need a nap. I would wake up at 9 after like chill a bit for 2 hours. I have to take a nap.
Did you guys go away or you stayed in town?
I went with my friends.
Where'd you go? Jealous? Well, you know, it was like minus 40 here, so it's almost the same. I can't believe it's January 22 and it's your first day of class. Isn't that nuts?
I have friends who were in CJEP and they have a month and a week off. Like don't even start till Thursday.
Well, when was your last exam? You guys had linear on the 21st, I think, right?
Yeah,
And today's the 22nd. That's a month. That's a month. That's a real month, especially since December is 31 days. You got the best month of the year. Yeah, who's not? And it goes by like you'll be tired by the time the break comes around. But,
I feel like this semester's gonna go by like really quick. This is like something before like the stash or like how many think about is that all of a sudden it's gonna pass by.
I got a whole bunch of you for this. I think I got all of you.
Yeah.
Do I have you?
Is it because of the recording?
No, it's not random at all. It's basically true.
That's gonna be fun.
There's only too many classes, so it's not hard to like juggle like 7 or 8 classes.
The schedule's actually fun.
Yeah,
What's that?
The schedule's actually fun. I ended
Fine.
at like 12.
Yeah, you're on Tuesday, Wednesday, Thursday I finish at 12.
Yeah, same here.
But Friday I finish with you at 5. That's gonna be bad.
At 5?
I've never finished at 5 before. Never.
Everyone in the stash comes up.
Yeah, I know,
That's
yeah.
my view. And we've decided, Jana, we, and Thomas and I, we decided that we're rarely going to have a lab meeting.
What do you got here?
Rarely, as in we'll try to keep it down to like once or twice.
We're
We're trying.
We just stay home. That's amazing.
Because no one wants to be there. Yeah. Yeah, we're trying to make it so that we never have to be there, but that would mean that we have to meet another time
Yeah.
during the week.
Or maybe, I don't, honestly, I wouldn't mind Friday morning.
It has to be a time where everyone's available.
That's true.
So it's probably gonna be around the lunchtime.
But just Friday start at 10.
Yeah, same. I think some people start at.
And even then, we don't need to meet every week. It's just like whenever there's something.
But what is the class about? Like, what's the whole point of the class?
It's not a class. Like, I
It's
mean,
just
it's
to
just a
keep up with
meeting.
your stats, that's it.
Yeah.
Alright.
It's like check-in kind of.
Yeah.
Because that's like for present research.
You guys have a cool one. You guys are working together, right?
Nope.
Who is it?
Didn't work
It didn't work out? What happened?
He said, yeah, he said, like it's way too short.
Yeah.
You're not gonna learn anything. He said minimum 3 months almost everywhere.
Where was this? It was a gaming company, right?
Ubisoft, there was CCO.
What are you guys doing next?
Denmark.
Denmark? Kentucky sounds pretty boring. Sorry. But Denmark, that's gonna be cool.
Big computer science. I'm working on like shipping like software for a company.
What are you doing in Kentucky?
Robots.
That's pretty cool.
That's cool. Yeah.
It's at the university. It's a research lab.
Robots are so sick.
Did you know there's more barrels of bourbon in Kentucky than there are people?
There are more what?
Barrels of bourbon than there are people. 95% of bourbon comes from Kentucky. Like, oh, fun stuff.
Where is that geographically?
But to the right now. Like something like this. Yeah, it's just, yeah.
But it's where is it? That's center?
Yeah.
Okay. So, here's what we're gonna do. Going back there. This thing, who's next? This thing there. This thing. So you guys have to fill it in when you get here. How many people are we to? 1, 2, 3, 4, 5, 6, 7. So missing 2 people. Missing the other Shah. And how's this part? Pretty sure. So he's just waiting for the other part?
No, I think he's still on vacation.
Oh, I see. Then, did you guys know if you registered for the thing?
Yeah, he did.
You did? Okay. All right. Okay, so what I want you guys to do is, Eric, we're an odd number, so there's going to be one group of 3 only. And what you guys are going to do is you're going to take a Slinky, and you're going to go to Moodle, download the Slinky lab, which is your lab 1, and you're going to do that activity. Okay, you can't go to the lab because there's some class going on in there right now. You'll have to do it here. You can push the tables aside, push the chairs away if you want, because you do need space for this. And I want you guys to play the Slinky. Now, look at this, Slinky. What do you notice about it? What I hold it like this? It's all together. Please give it back to me, that one. Right? Please. Tanya will kill me. All right. Okay, so do that. I have 8 Slinkies. Does that work out? That works out perfectly. So you got a crappy one. Oh no, you know what? I didn't work.
Can we take a 3-man team?
What's that?
Can we have a
Yeah, so the 3-man team has been claimed.
Yeah, I remember this in so long.
Yeah, you go.
Oh shit, I broke
One thing that you could do to make this easier is work on the ground. Like if you have this Slinky resting on the ground and you do movements like this or like this, it's probably going to be better, My recommendation. Mind-boggling.